Hello everyone, welcome to another kinetic tutoring video. Today we're looking at another FRQ problem from the 2024 AP exam. So let's get straight into it. We're looking at a sphere of mass m that is falling through the air straight down, and the forces that are acting on it are gravity and drag force. So we're trying to find a differential equation that could be used to determine the speed v of the sphere as a function of time t. So what we're going to start with is our force equation, ma, which is our net force, is equal to mg, our gravity force. We're going to say that downwards is the positive direction, minus the drag force, since the drag force is going upwards, minus bv. And to find our acceleration, we're just going to divide both sides by m. We get g minus b over mv. And finally, we know that a can be written as dv dt. So here we get dv dt is equal to g minus b over mv, and here is our differential equation. So that's how you would go about solving part 1. Let's move on to the next section. Student sketches the drag force Fdrag exerted on the sphere as a function of time t as shown in figure 2. Draw a vertical line in figure 2 to indicate the earliest time at which Fdrag is equal to the magnitude of the weight of the sphere. So the key term here is terminal speed, and as we can see here, it reaches terminal speed when Fdrag starts to even out. So our line is going to be here. This isn't a great line. Let me actually redo that and use the line tool provided to me. It would look something like this. That isn't perfect, but they don't really expect perfection, so it's fine. And it says justify the location. So if we look back at our differential equation, dv dt is equal to g minus b over mv. We can see that as this force here, as the velocity increases, the dv dt, or the acceleration, is going to decrease. So, we know that our, let me try to restart that. Okay, so we know that our Fdrag is equal to bv. So we know that as time goes on, our velocity is increasing, meaning that our Fdrag increases until it reaches terminal velocity, and at that point it starts to even out, which is what we notice here. So it starts at velocity 0, so Fdrag is 0, and then it ends at velocity vt, where our Fdrag reaches the point bvt. There we have it. Now let's go to the next part. Alright guys, it says, suppose the student throws the same sphere downward with the non-zero initial speed. Magnitude of the new drag force at the terminal speed after being thrown is F nu. Indicate whether F nu would be greater than, less than, or equal to the magnitude of Fdrag at terminal speed. So we know that terminal speed is when our equation here is no longer accelerating. So when we have this equation here and it's no longer accelerating, this becomes 0. So you get mg minus bv, and mg, that makes mg equal to bvt, where vt is your terminal velocity, meaning that your terminal velocity is equal to mg over b, where m is the mass of the mass of the sphere, which does not change. G is our gravity, which obviously is not going to change, and b is the coefficient that has to do with the level of how aerodynamic our ball is, which also has not changed within the experiment. So due to all these factors staying the same, our terminal velocity is going to stay the same as well. And since our terminal velocity stays the same and our coefficient of B stays the same, Fdrag is also going to be the same at terminal speed. Alright, let's head to the next part. Here we have the student conducts a measure to better understand the relationship between Fdrag and V. The student makes measurements to calculate the graph Fdrag as a function of V falling for the sphere. Draw a best fit line for the data and use a best fit line to calculate an experimental value for B. So let's do that now. Here's a rough best fit line. You're going to want to use a ruler or straight edge when you do this on an official exam, but this is decent. As we can see here, the slope is somewhere around 3/4. We're going to say that the slope is 3/4. And here we have Fdrag, which is BV, and here we have V. So we know that Fdrag is equal to BV. So Fdrag over V, which is what we have graphed over here, is equal to B. And since we said that Fdrag over V, the slope is going to be 3/4, we can say that our B is approximately equal to 0.75. Alright guys, here we have the final part of FRQ2. So let's get right into it. The student has access to but does not use all of the following equipment. Oh, sorry, let me read the first part. A student claims that the terminal speed Vt of the sphere depends on the diameter d of the sphere. The student designs an experiment to collect data that can be used to provide evidence to support the claim. The student has access to but does not have to use all of the following equipment. Sphere set 1, spheres of the same known mass with different diameters. Sphere set 2, spheres of the same known diameter with different known masses. A motion detector that can measure velocity as a function of time. And now indicate the two quantities that one graph could be used to determine whether the diameter of the sphere affects the terminal speed. So I think the logical option here would be to use the two variables that are mentioned in the prompt, which is the diameter and the terminal speed. We know that usually you want to use the dependent or the independent variable on the horizontal axis, which is the diameter. So here we go, diameter here. And you know that you want to use the dependent variable on the vertical axis, terminal speed. And now briefly describe how the quantities graph could be used to determine the relationship between the sphere diameter and terminal speed. So guys, the way I went about this problem is looking at the forces once again. We know that at terminal velocity, mg is equal to bvt. And we know that, just thinking about a ball and how aerodynamic it is, when we have a ball that's the same mass, we have different balls that are the same mass but they're expanding in diameter. If you think about it logically, as a ball expands in diameter, it's going to become less and less aerodynamic, and it's going to be more likely to feel air resistance forces more because there's more of a surface to be affected by air resistance. So we could say that as the diameter goes to infinity, our B is also going to go to infinity. And we know that our mg is going to be some random constant, so we'll just call mg c. And we have B, which is approaching infinity. And as B approaches infinity, our velocity is going to be equal to 0, or our velocity is going to be approaching 0. So when we're graphing diameter versus velocity, we can see here that the terminal velocity is going to have an initial value depending on the mass of the ball you begin with and the radius, and as it progresses, it's going to the terminal velocity is going to decrease as the diameter of the ball increases. That's how I went about it, and that's the solution I came up with. There may be other ways to solve this problem, and another more convincing way you could explain your answer is by just writing this equation a little bit differently. We know that since we want v of t over b, we can say that our mg is equal to v over b to the -1, just to make your answer look a little bit more sophisticated, since we know that this is going to be related to the slope. That's all I have for you guys today. Thanks for watching, and I hope this helped. And make sure to tune in again for more kinetic tutoring tutorials.